Hello everyone and welcome to Pre-Calculus Algebra Lecture 16. Today we're going to be talking about rational functions. A rational function, and we'll denote this as capital R of x. A rational function is the quotient of two polynomials. So in other words, if R of x is a rational function, we can express it as the polynomial p of x divided by the polynomial q of x, where p of x and q of x are polynomials. So let's look at some examples. The first example, the numerator is a polynomial, the denominator is a polynomial. Check, it's a rational function. The second example, the numerator is a polynomial, the denominator is a polynomial. Check, it's a rational function. In the third example, yes, the numerator is a polynomial, the denominator is a polynomial. Check, it's a rational function. In the fourth example, we have a numerator over a denominator. And I think, well, what do you think about this one? I think we're going to have to disallow it. And here's why. Maybe you've already figured it out. The numerator is a polynomial. Check. The denominator is not a polynomial. This square root of x is the disqualifying factor, so to speak. Square root of x is the same as x to the 1/2 power. So this term, square root of x, is not a monomial. And you remember we defined polynomials to be the sum of monomials. Well, if we write square root of x to something raised to a power, it's x to the 1/2 power. The exponent is not a non-negative whole number. So this thing here disqualifies the expression from being a rational function. What about the domain of a rational function? That is, the set of x values that are fair game to plug into the function. Well, in order to determine that, we'll go back to the method that we were using to find the domain of functions in general. Do you remember what that was? The first thing that we would do is assume that the domain is the entire set of real numbers, right? So assume the domain is the entire set of real numbers. And the second and third steps, I don't remember which one came first. I think it might have been exclude all x values that cause division by 0. And then the third was exclude all x values that yield a negative under a radical, or some expression with an even root, square root, fourth root, sixth root. Here, we don't really have to worry about this because a rational function is the quotient of polynomials, and polynomials don't have any radicals. Polynomials don't have any square roots, cube roots, fourth roots, and so on. So this step, we don't have to think about when we're determining the domain of a polynomial. So assume the domain is the entire set of real numbers. Exclude all x values that cause division by 0. So the domain of a rational the domain of a rational function is the set of all real numbers that don't cause division by 0. That's the domain of a rational function. So let's look at a few examples. Find the domain of each rational function. This is a rational function. It's the quotient of two polynomials. And we assume that the entire set of all real numbers is the domain. And we'll exclude any x value that causes division by 0. So let's see. Let's set x plus 3 equal to 0. And solve. And we get x equals negative 3. We will exclude this x value from the domain because it causes division by 0. So the domain are all the real numbers from negative infinity to negative 3, not including negative 3. And all the real numbers from not including negative 3. And all the real numbers from negative 3 to positive infinity, not including negative 3. And remember, the fact that we have these round parentheses next to negative 3 indicates that negative 3 is not included in this set. So the domain of this function is the set of all real numbers except negative 3. And somewhere along the way, the authors of our book decided that they were going to start writing this in a different way. This is how they write it. This is how they write it. And this is how we view this expression. This much is translated this way. The set of all real numbers x, that's what this much of it means. This vertical bar is translated such that, and then the condition for membership into the set. So this is the criterion or the condition for membership. What does a real number x have to do so that it gets into this set? The real number x simply can't be equal to -3. So we look at this and we say it's the set of all real numbers x such that x is not equal to -3. And I'm mentioning this because our authors may prefer us to write it this way rather than this way. Although if you write it this way on a test, I'll be happy to accept it. And what about this polynomial, or this rational expression? It's the quotient of polynomials. X plus 3 is a polynomial. X to the 4th plus 1 is a polynomial. What is the domain? Again, we assume that the domain is the entire set of real numbers, and then we exclude any x value that causes division by 0. So let's look at the denominator and see if there are any x values that make this denominator equal to 0. And we get x to the 4th power equals -1. There are a couple of ways that we can reason on this. One way is to remember that x to an even power can never be negative. And I should qualify this. A real number x raised to an even power can never be negative. A real number x raised to an even power can never be negative. So that's one way that we could come to this conclusion. Another way is this. That we could take x to the 4th equals -1 and say x to the 4th, isn't that x squared squared? We can't take a real number and square it and get a negative number. So this is impossible. A real number squared cannot be negative. We set out to exclude all x values that cause division by 0, and there were none. So I'll just mention that. No x value causes division by 0. So domain equals the entire set of real numbers. We can mention it like, denote it like this, or we can say all real numbers. We can do it like that. Oftentimes, but not always, rational functions have something called asymptotes. So we'll look at the definition of an asymptote right now. Given the graph of f of x and a line L, the line L is an asymptote of the graph of f of x if, as we move along the graph of f of x, the graph gets closer and closer to the line L. So the line L is an asymptote of the graph of f of x if the graph gets closer and closer and closer and closer to that line L. And if that's the case, we can also say that the graph of f of x is asymptotic to the line L. Let's look at some examples, some pictures, so that we can make better sense of this definition. Here's a nice example. That we have a vertical line given by x equal 2. We have a horizontal line given by y equal 1. And I claim that both of these lines are asymptotes. As a matter of fact, I'm going to write that down right now. This line, x equal 2, is a vertical asymptote. Any asymptote that happens to be a vertical line is a vertical asymptote. That's easy enough that even I can figure that one out. So x equal 2 is a vertical asymptote. This line right here, y equal 1, it's a horizontal line. And you guessed it, we call that a horizontal asymptote. And now let's make sure that we see exactly why each one of these lines is an asymptote. I'm going to start at a point right here, just a random point, and I'm going to move along the graph in this direction. And as I do, the graph gets closer and closer and closer to the line y equal 1. So the line y equal 1 is an asymptote. And since it's a horizontal line, we say it's a horizontal asymptote. Also note this. Suppose I start on an arbitrary point on this part of the graph, and I move in this direction. I start on the graph, and I move in this direction along the graph, and as I do, the graph gets closer and closer and closer to this line y equal 1. Again, the graph gets closer and closer and closer to y equal 1 as we move along the graph in this direction. And again, the graph gets closer and closer to the line y equal 1 as we move along the graph in this direction. So the line y equal 1 is a horizontal asymptote. Now, what about the verticals? Suppose that I start on this same exact point, but I go in the opposite direction. I'm moving along the graph in this direction now. And as I do, the graph gets closer and closer and closer to this vertical line x equal 2. That means that the line x equal 2 is a vertical asymptote. And if I were to start at a point on the graph, this part of the graph, and move along the graph in this direction, notice again that as I move along the graph in this direction, the graph gets closer and closer and closer to the line x equal 2. So x equal 2 is a vertical asymptote. Another example. This graph has some asymptotes. Can you pick them out? As far as horizontal asymptotes, the line y equal 1 is a horizontal asymptote. And here's the reason. If I start on the graph right here at this point, or any point around here, and I move in this direction along the graph gets closer and closer and closer to the line y equal 1. So that makes y equal 1 a horizontal asymptote. Over here, the same thing happens. If I start at a point on this portion of the graph, and I move along the graph in such a way, if I move along the graph in this direction, the graph gets closer and closer and closer to the line y equal 1. So the line y equal 1 is a horizontal asymptote. Now you may be wondering, does the fact that the graph crosses the line y equal 1 right here void the claim that the line y equal 1 is a horizontal asymptote? Not at all. Typically, asymptotes don't touch the line, but it can happen. Here's a case where the asymptote crosses the line. This does not void the warranty, so to speak. And what about vertical asymptotes? X equal 2, that looks like a good candidate. And x equal negative 2, that looks like a good candidate. For example, if we started a point on the graph right around here and move along the graph in this direction, the graph gets closer and closer and closer to the line x equal negative 2. So the line x equal negative 2 is a vertical asymptote. And it's also true that if I were to start on a point on this part of the graph and move along the graph in this direction, again, the graph would get closer and closer and closer to the line x equal negative 2. So x equal negative 2 is a vertical asymptote. And the same thing happens with x equal positive 2. If I start at a point on the graph right around here and move along the graph in this direction, the graph gets closer and closer and closer to the line x equal 2. So we'll add x equal 2 to our list of vertical asymptotes. And as supporting evidence, if we pick a point on this side of the asymptote x equal 2 and move along the graph in this direction, again, the graph gets closer and closer and closer to the line x equal 2. So these are our vertical asymptotes, and y equal 1 is our horizontal asymptote. Okay, here regarding rational functions, we wanted to find something an expression lowest terms. A rational function, p of x over q of x, is in lowest terms exactly when p of x and q of x have no factors in common other than plus or minus 1. Now this expression, lowest terms, is borrowed just from fractions. A fraction p over q is in lowest terms if they have no factors in common. Other than plus or minus 1. So let's see. 3/4, do they have any factors in common other than plus or minus 1? No. So 3/4 is in lowest terms. Now what about this one? 6/8. Is this fraction in lowest terms? We look at it and say, no. Both the top and the bottom have a factor of 2. 2 times 3, 2 times 4. And we say, okay, this is not in lowest terms. So what do? We cancel out the common factor. And now we have a fraction in which the numerator and the denominator have no factors in common other than plus or minus 1. So this is now in lowest terms, but the original not in lowest terms. And we apply this same concept to rational functions. If they have some factor in common other than plus or minus 1, then they're not in lowest terms. If they don't have any factors in common other than plus or minus 1, then they are in lowest terms. So let's look at these two rational functions. Do they have x in common? Nope. Is 4x minus 5 a factor of the numerator? I don't think so. Do they have any whole number factor in common, like 2 or 4? Doesn't look like it. This appears to be in lowest terms. But now what about this one? Does anything jump out at you as far as being a common factor? Every term in the numerator has a factor of x. Every term in the denominator has a factor of x. Oops. This is not in lowest terms. And the reason is we can write this, the numerator is x times 3x squared plus 4x minus 1. And we can write the bottom as x times 4x minus 5. Numerator and denominator have a constant factor of x, a common factor of x. Now, if we were to cancel those out, we'd get 3x squared plus 4x minus 1 over 4x minus 5. And now that we've gotten rid of the common factors, we can say in lowest terms, this is a subtle point that I probably should mention. And it's best illustrated by an example involving two closely related functions. We want to find the domain of each rational function. So we assume that the domain is the entire set of real numbers, and then we exclude any real number that causes division by 0. So we'll set the denominator equal to 0. X equal 5 causes division by 0. So x can't equal negative 5. X equal 5 is not in the domain of R of x. And you know what? Just to avoid any further confusion, let me change the name of this second function. Let me call this second function S evaluated at x. So here's the domain. The domain is the set of all real numbers except 5. And we can write this a different way. The set of all real numbers x such that x is not equal to 5. That's the domain. Now let's look at this second function. We assume that the set of real numbers is the domain of this function. And then we exclude any x values that cause division by 0. So we take the denominator and we set it equal to 0. We have the product of two things equal to 0. So that means that either the first thing is 0 that means that either the first thing is 0 or the second thing is 0, which means x equals 0 or x equals 5. X equals 0 and x equals 5 cause division by 0. We have to exclude them. So here's the domain of this second function. The set of all real numbers other than 0 and 5. And we can write it this way instead. The set of all real numbers x such that x is not equal to 0 or 5. That's the domain of the second function. But now we might wonder about something. We might look at this function and say, you know what? It is not in lowest terms. Maybe we should cancel out the common factor first. So what would happen if we did that? If we took s of x and we factored out the x in the top, and we factored out the x in the bottom, and then canceled the x's, we'd get this. And this turns out to be our function r of x, the one that I so prudently erased just a minute ago. But we already found out that the domain of this thing is the set of all real numbers except 5. Set of all real numbers x such that x is not equal to 5. So isn't the domain of this function s of x really just all real numbers except for 5? Because after all, when we take s of x and cancel the common factor in top and bottom, we get the function that has a domain of all real numbers except x equal 5. So can't we do that? And the answer is no. Part of the problem here is that when we divided top and bottom by x, we did this with the agreement that x can't be 0 because we can't divide by 0. So when we divided top and bottom by x, which is what we were doing when we canceled, we did that with the understanding that x is not equal to 0. So this thing and this thing are only equal as long as x is not 0. If x is 0, then this is how we have to define s evaluated at x. And 0 is one of those numbers that's not in the domain. This is how s evaluated at x was defined. And if we plug in x equals 0 here, what do we get? We get 0 over 0. It's undefined. But if we plug in x equals 0 here, what do we get? Negative 1 over negative 5, which is 1/5. So this function and this function are not exactly the same. This function can't have x equals 0 in its domain. This function can have x equals 0 in its domain. The point is, if we take a function that is not in lowest terms, and we cancel a factor from top and bottom, we have to keep the domain of the original expression. We can't change the domain by dividing top and bottom by a common factor. So if the definition of the function is not in lowest terms, and we exclude an x value, x equals 0 in this case, as a consequence of the fact that the expression is not in lowest terms, the domain of the function is not going to change when we divide top and bottom by that common factor. we have to keep the domain the same. Just a technicality. Let's take a look at some common functions having asymptotes. And before I get too far into this, let me just correct the second one. Both functions are 1 over x to the n. And in the first case, n is odd and a positive number. So 1 over x raised to a positive power, where n is an odd number. The other is 1 over x to the nth power, where n is an even positive number. We want to know what the graphs of these two functions look like, because both of these functions are typical of functions that have asymptotes. So let's look at 1 over x to the n, where n is odd first. First, let's study the graph f of x equals 1 over x to the n, where n is odd and positive. And we remember our old friends. X equals -1, x equals 0, x equals +1. And when x is -1, -1 to an odd power is -1. So we have 1 over -1 is -1. So the point -1, -1 will be a point on the graph. When x is 0, we have 1 over 0 to the n. Oh my goodness. When x is 0, we're dividing by 0. So when x is 0, there's no point on that graph. What about x equals +1? 1 over 1 to the n power is 1. This is what the graph looks like. And notice that the y-axis is a vertical asymptote and the x-axis is a horizontal asymptote. The same thing happens to this portion of the graph to the left of the y-axis. The y-axis is a vertical asymptote. The x-axis is a horizontal asymptote. Know this graph. Now let's look at the case where n is even. So why do we look at this case? Well, we're going to generalize this to graph other functions. And graph this 1 over x to the n, where n is even and positive. that we look at our old friends again. X equal -1, X equals 0, X equal +1. And when X is -1, we have -1 to an even power, so that's +1. 1 over +1 is 1. So the point 1, 1, no, the point -1, +1, is a point on the graph. And when X is 1, we have 1 over 1 to the n power. So that's 1 over 1. When X is 1, f of X is 1. And when X is 0, oops, we have undefined. So 0 is not in the domain. I should have erased this from before, but I think I'll keep it. I think things are going to look similar. The x-axis is a horizontal asymptote. The y-axis is a vertical asymptote. This is what the graph looks like when n is even. And we want to use this as a model for when we graph variations on the function f of x equals 1 over x to the n. So know this graph also. This looks like a good one to start off with. Graph f of x equals 3 times x squared. The basic graph that I'm going to start out with is just 1 over x squared. I'm going to graph that. And I remember that it has key points, -1, +1, and +1, +1. And it has the x and y axis as the asymptotes. So that's what it looks like. Three over x squared. Isn't that the same thing as 3 times 1 over x squared? So we're just multiplying 1 over x squared by 3. So this is vertical stretching. Horizontally, everything stays the same. Vertically, things get stretched. So let's see how that comes about. -1, +1, 0, 0, 1, 2, 3. The y-coordinate of this is 1, but we're going to stretch that vertically by a factor of 3. So on this graph, the corresponding point is -1, y equals 3. And you know what else I'm going to shift up? I'm going to shift the definition of. There we go. Now, this point, x equal 1, that's going to stay the same. Y equal 1, the y factor is going to get stretched by 3. So the point on the new graph that corresponds to this point is going to have a y coordinate that's 3 times greater. The x and y axis are still going to be asymptotes. So now we're going to have this sort of thing. Boy, that's a horrible graph. I apologize. You know, I applied to get into art school once and I couldn't get a scholarship. I was so hurt. But I guess I shouldn't have been. I think they knew what they were doing. So this is the graph of f of x equals 3 times 1 over x squared or 3 over x squared. Let's do one more variation.